things you can do is to compute the area of a parallelogram. If you have, oops, in three-dimensional space, two vectors, and you take one of the vectors and put it at the end of the other, and then the other one and put it at the end of the first one, you form a parallelogram like that. And you can ask, what is the area? Well, think about it for a second. Let's draw it like this just for convenience. This one, if this is the vector A, has length of A. This one has length of B. And what is the area of the parallelogram? Well, you can drop a perpendicular right here, and this little triangle fits right in here. So the area of the parallelogram is actually the same as the area of this rectangle. But what are the dimensions of the rectangle? Well, the rectangle has length of A for the length here, but then the height of the rectangle is what? If this is the angle between the vectors, then you know this side from trigonometry has to be length of B sine of theta, where theta is the angle between them, right? So that this over this is the sine of theta. So the rectangle has side lengths A length and B sine theta length. So the area of the parallelogram is length of A times length of B sine theta. Well, what's that? That's just the length of the cross product. So there's the proof that you can find the area of a parallelogram by using the cross product. Moreover, it does something even more fundamental. Suppose I cut this parallelogram in half like that. Now, what's the area of this triangle? What's the area of the triangle? Well, by symmetry, you can flip this over and over, and it's exactly 1/2 of the parallelogram area, so the area of the triangle is 1/2 the length of A cross B. This means that you can find actually the area of any polygon in space just by triangulating, or cutting triangles out of it and adding them all together using this cross product. So kind of a neat result. You can find the areas of parallelograms and of triangles using the cross product. Here's an example. Suppose I took the two vectors in three space, A equals 1, minus 2, minus 1, and I took B to be the vector 1, 0, 1. Find the area of the triangle they determined. Just for fun, we can draw it, right? We can come over here. 1, 2, minus 1. So we go 1 in the x direction, minus 2 in the y direction. And we can draw this kind of a parallelogram in the xy plane. And minus 1 in the z direction. So we go down 1 also. And remember, the vector then goes from the origin to the far corner of the box. The vector A looks like that. Now the vector B is 1, 0, 1. This lies in the xz plane, so it's a little easier. Right? So we go 1 in the x direction and 1 in the z direction. And here's the vector B. Now we want to take A cross B, so we're going to get something pointing out in this direction. By the right-hand rule. But suppose we just wanted to find the area of the triangle that A and B determine. Suppose we wanted to find the area of this triangle right here with A and B for 2 of the 3 sides, and then you connect the endpoints. what is this area here of this triangle determined by A and B? We simply say that it's 1/2 the length of A cross B, which is 1/2, and we'll put these into the determinant formula, the one that's easy to memorize. I, J, K, 1 minus 2 minus 1, 1, 0, 1, length. Well, you compute this cross product by saying, well, I multiplies minus 2 minus 0, so it's 1/2 the length of minus 2I. And then minus j multiplies 1, minus 1 is 2. So we get minus j times 2. And then k multiplies 0 minus a minus 2 is 2. So we get plus 2k. And we want 1/2 of this length. Well, the length is the root sum square of those, which is 2 square root 3. So we've got 1/2 2 square root 3, or square root 3 is the area of the triangle that these two vectors form two sides of. So that's an application of the cross product, is finding areas. Another application is for volumes of parallel pipets. The volume of the parallel pipet with three sides determined by vectors. Here's A, here's B, and here's C. I form the parallelogram with A and B, and then I form a parallelogram with A and C. Oops, I'm sorry, this is not. Oh, this one A, C, and B. The parallelogram with A and B, the parallelogram with A and C looks like this. And then I fill it out and I make a six-sided figure, like a six-sided die is a special case of this where you have right angles. And here's the rectangular parallel pipet. What is its volume? Well, if you think about it a little bit, this has to be the absolute value of A dot B cross C, actually. Because what you do is you take the area of the base times the height, which is the length of A times the, so the area of the base with B and C times the height times the cosine of the angle between them. There's a nice picture in the book. And this comes out to be the volume formula for the parallel pipet. We call this the triple scalar product, sometimes written as A, B, C. It comes up so often that it has its own notation. You have to do the cross product first, because the cross product gives you a vector that you can dot with this one. If you did the dot product first, you couldn't cross it with anything because you have a number, not a vector. So the volume of a parallel pipet is actually the absolute value of this scalar triple product, A dot B cross C. There's a nice example here we can do. here's a rectangular parallelepiped. Oops, maybe it's not there. Okay. Alright, so let's see if we can calculate a volume here. Suppose I consider A to be the vector 1, minus 1, 2, B to be the vector 0, minus 1, 1, and C to be the vector 2, 1, 3. Find the volume of the parallelepiped that they determine. Well, you just have to take A dot B cross C, absolute value. Well, it turns out there's a fast formula for this. Note, if you take A dot B cross C, what are you doing? You're taking A dot, this determinant, I, J, K, B1, B2, B3, C1, C2, C3, and the dot product is going to take A1 with the first component of this, which multiplies I, A2 with the second component that multiplies J, and A3 with the third component that multiplies K. So this is equivalent to just putting A1, A2, A3 in the first row. Now A1 will multiply the first component of this, A2 the second, and A3 the third. Consequently, this is a fast formula for the scalar triple product. It's just the determinant. So that determinant has that nice interpretation. It's the scalar triple product. Gives you the volume of a parallelepiped volume, of a parallelepiped. So let's do it for this one. We want the volume is the absolute value of the triple scalar product. I'm going to, because the absolute value is straight bars and the determinant is straight bars, there's a conflict of notation there. Let's say that the volume is ABS for absolute value of the triple scalar product, and we put these into the rows. 1, minus 1, 2, 0, minus 1, 1, and 2, 1, 3. So we'll take this determinant, putting the vectors into each of the rows, and then take the absolute value when we're done, and that'll give us the volume. Well, the determinant is 1 times, minus 1 times 3, minus 1 times 1, right? This number times its subdeterminant gotten by wiping out its row and column. And then minus the second element, minus 1, times its subdeterminant. We wipe out its row and column, and we get, let's see, 0, 1, 2, 3. And then plus the element, the last element in the first row, times its subdeterminant, wipe out its row and column, 0, minus 1, 2, 1. So we get, evidently, I should have put this one the same. Let's leave this as determinant for now. So it's 1 times its subdeterminant, minus 1, 1, 1, 3. And then each of these 2 by 2 determinants is diagonal minus diagonal. So this is 1 times minus 3, minus 1 is minus 4. And then plus 1 times 0, minus 2. And then plus 2 times 0, plus 2, minus or minus 2 is, 2 times 2 is 4. And oops, plus 2 times 2 is plus 4. Oh boy. evidently it's equal to -2, the 4 and the -4 canceling. And absolute value of all that. Oops. So its absolute value of this, the volume must be 2. So there's an example of finding the volume of a parallelepiped. There's a nice property that this scalar triple product has also that we should mention. If you take A, B, C in the triple scalar product and rotate them around, it has the same value, actually. This is equal to C, A, B is also equal to B, C, A. So rotating these around gives you actually the same value. After all, if you think about it, it's just rotating all the rows of the matrix around. However, what happens if you've seen linear algebra before? What happens if you interchange two rows? So like instead of A, B, C here, I put A, C, B, interchanging these two. This makes minus the value of the determinant. So if you interchange two rows in a matrix, in fact you know from matrix algebra or just from the determinant formula, it's easy to prove, you get minus what you would have had in the original order. So this one is actually equal to minus this one, and then you can rotate these around. It's minus C, B, A is minus B, A, C. So there's 6 different orders you can put A, B, C in. 3 of them are equal, the other 3 are equal, and the one triples are all equal to minus the other triples. Well, that'll be probably enough for today. Try these problems in here and see if you have any questions.